Alright, grade 12. Here we are looking at a worked example for 9.3, which is where the recurrence relation is going to rear its head again as we look at this example of an annuity. So here we've got at the end of each year, now that's key, so I'm going to actually underline that for a second, $1,000 is invested at 5.75% per annum and it compounds once a year. A is to set up a recurrence relation that represents the value of the annuity after each payment is made. So if you remember from earlier, and this will be on your formula sheet too, our annuity is A, well, let me go to subscript, I might have to quickly just put this in, sorry. Do it properly this time. So we've got A, n plus 1, okay, I might zoom in a tiny bit for this. A, n plus 1 is going to be equal to the common ratio, oops, still in subscript, sorry. There we go, equals R times A, sorry, I've got to use script again. A to the N. In this case, it's going to be a common difference, and I'll tell you why. Okay, now, as I highlighted earlier, at the end of each year, $1,000 is invested. So when you think about those, however many years we're doing it, that very first year, there's actually going to be nothing deposited. Okay, so in that case, what we have to do is we have to work out what A is equal to, that it is our, what our starting value is. Okay, now in this case, they're depositing $1,000. $1,000 every year as their payment. So therefore, I would say that's not A1, sorry, A0, the very kind of starting amount is going to be $1,000. That's what we end up with, okay? And the common difference is obviously equal to $1,000 as well. So how we go about doing that? Well, I'm going to copy and paste this down. So here, to work out our value after 1, we substitute these values in. Okay, now the rate is what we have to work out. Here it's 5.75% per annum compounding annually. It all lines up, so we can actually just times it by 1.0575. We didn't need to do any division beforehand because it all made sense. It all lined up. Okay, we're told what A0 is, so that's going to give us 1,000. Now, we're going to think about this logically for a second, okay? Because effectively what I've worked out up here, just going to put this here and explain it another way. Instead of saying A0, we can actually call this amount at the end of year 1. Okay, the amount we have at the end of year 1 is $1,000. Now you're probably sitting there thinking, but hang on, why hasn't that got any interest? And that's because, going back to my underline section, at the end of each year, $1,000 is invested at 5.57% per annum compounded annually. Okay, so that's why we only have $1,000 at the end of the first year. Now, think about what this is now calculating. This is now going to calculate the amount that we have at the end of the second year. Okay, so we're actually into answering part B now, all right? And we're trying to find the first 4 years. So when we actually want to find the first 4 years, we're looking for A0, A1, A2, and A3. We won't actually need to do A4 because A0 is going to give us the amount after the first year, then the second year, the third year, and the fourth year. It answers it all for us, okay? Now, going ahead with this one, okay? We put this into the calculator, and I just realized I don't have my calculator out. Let me just grab it. 1.0575 times 1,000 plus 1,000. What that's going to do, just copy and paste this down again. It's going to give you A1. We don't need the A0 there anymore as well. I might just quickly backtrack that here. So putting that into the calculator, we get 1,000 put units in, $1,057.50. Okay, that's what we end up with at the end of that year. Okay, using our recurrence relation. Now that we've done this one, let's go back to our original recurrence relation. So instead of writing, for those who are still confused, A1 is actually going to give us the amount at the end of year 2. So here's our recurrence relation. I'll just fill in the blanks. AN plus 1,000. What we're now going to work out, so we've just worked out A0 plus 1. We can go A1 plus 1, and now the n here will be 1. And I just realized I didn't add the $1,000 to that. That should be $2,057, sorry. So here's our recurrence relation. We've substituted the values that we will know here. So this is going to be multiplying by $2,057.50. Okay, we pop this in. This is going to give us A2. Another word, as we've just discussed for A2, remember, is the amount at the end of of year 3. So putting that in. Now remember, as I said earlier, the reason we're plussing 1,000 and not calculating interest on that 1,000 is because it's added at the end of the year. Okay. The amount at the end of year 3 is going to equal $3,157.80 for that one there. And finally, what we have to do now, put my recurrence relation down here. I'll zoom out a little bit now so you can see the whole thing. Whoopsie daisy. There we go. So now what we're doing is we're going to do A2 plus 1. That means we're going to need A to the 2. Okay, so far so good. Just making a bit more space, sorry guys. Alright, so copy and paste this down. So now we're working out A to the 3. That's now going to be multiplied. A2, our value for A2 was 3157.8. Okay, and we put that into the calculator. $4,358.52. Sorry, 42 cents that should be. Okay, so therefore we can now answer part B. Probably easy just to autocorrect. $4,358.42 after 4 years. I've already went over the logic of why we only went to A3. It's because we included A0. Okay, so remember, instead of writing A3, the other way to remember it is the amount at the end now of year 4. So there is our answer for that one. Okay, so now looking at our next question, we've got using technology, determine the future value of an annuity of $250 invested every 3 months, that's quarterly, at 5.75% per annum, compounded quarterly. Now, for A, please refer to the Excel document. That's where we're going to be doing these, okay? So, what I've gone ahead of time and done is set up this part. Now, I've got a quarterly, a half yearly, and an annually. Okay, this is for part B, and technically this will also be part A over here. Bit of an abstract order to do it, but it'll all work out. Now, going back here, okay, we've got determine the future value of the annuity after 6 years. Now, this is where students kind of get a bit stuck, and why I've purposely set it up this way. So, what we have, when we have a quarterly annuity, we start with period 0, okay, and then we'll keep on going. So I'm just going to expand these out a little bit. Now, because it's quarterly, we're going to go a bit larger than this, and I'll show you why. How we set up our recurrence relation, because that's what we're dealing with here, recurrence relations. Just like our previous example here, our A0 is generally the amount at the end of the first period. This period here worked in years, so is at the end of the first year. This one's working every 3 months. So our A0, 3 months are going to pass, and I'll quickly just put that in here. The time for each of these is going to be in months. I'll just quickly fix these up as well. And to keep it simple, $250 was invested, okay? Makes it nice and easy. I'll just widen these a little bit, okay? Now, after one period has now passed, isn't that just going to be 6 months, then 9 months, and we can go on from there. Now, the question is actually asking, let's count it out. Determine the future value of the annuity after 6 years, okay? And 6 years, that's 72 months. We are nowhere near 72 months, so we need to expand these sections to about here. There we go. So now we're all the way down to 72 months. That's going to be 6 years. If you're wondering why I didn't use years, it's because of the compounding quarterly. Now, I could have said, okay, instead of 3 months, I can write it as 0.25 years. Nothing's stopping me doing that, honestly. I could have, but I thought I'd express it as months. You just need to have that understanding that the 72 months is the 6 years. Now, let's have a look at how our recurrence relation is going to set up in Excel. Okay, we know it's a n plus 1 is equal to the ratio. Now, let's start with that ratio. Our last one was a little bit easier. Okay, always start with your equal sign. Now, to work out, or to get our previous one of 1.0575, we just added 1 to that as a decimal. We can't do that in this example though. Okay, and I'll tell you why. Because this 0.0575, I might just widen, no. Oops. Widen it, I'll start again, sorry. So, equals 1 plus 0.0575. The reason we can't do this, grade 12, is because this 0.0575 is the interest rate every year. We are not working in yearly amounts like we were in question 1, as you can see here, at the end of each year, and it was compounded annually. Okay, now we're dealing with 250 and it's compounding quarterly. So what we need to do is actually divide that by 4. Now the way BOMDAS will work, it'll work out a quarterly rate and then add it to the 1. Now what we're going to do is times it by the amount from the previous section, okay, how much we had previously. And then what we're going to do is we're going to add our constant rate. Now the constant rate we're depositing here is $250. Okay, and that's going to spit out $503.59. Okay, I might just change a couple of these rows to currency. Oops, that's number. There we go. Got our units there now. And what we can do is, if we've done it correctly, we should be able to drag and drop. Just before I do though, let's see if this makes logical sense. Okay, with the annuity, we know that after every 3 months, we deposit $250. Now, obviously, we don't earn any interest on the first one because we don't deposit it until the very end and we don't get a payment out of it. But after this one, this $250 has been sitting in there for 3 months. That should be accruing some interest. Okay, notice this second lot of $250 in the formula isn't. Okay, but this first lot will, hence why we're timesing by the cell here. All right, so going back to this, what we should be able to do now is drag and drop. And there we go. What we've now done, and as you can see, I'll just quickly cycle over them. All of the cells are staying constant, all the numbers, sorry, are staying constant. The only thing that's changing is that cell, because it is compounding, okay? That amount is going to continue to grow. So there is our answer for part A, okay? And this, as I said, this is all obviously on style, readily available for you. So there is our future value there, and I'll just highlight that now for you. Okay, so part A answer. Let's read part B. Construct a graph that compares the future value of the annuity at an interest rate of 5.75% per annum. So notice how the rates are the same for the following investments. So we've got $1,000 being invested every year and compounded annually. $500 being invested every 6 months, compounded half yearly. $250 invested every 3 months, compounded quarterly. Okay, so first things first, you'll notice these actually all share an amount in common. If I invest $1,000 a year, that's the same as investing $250 a quarter. So theoretically, the money that we're actually depositing here, the $250, the $500, and the $1,000, is actually all the same in terms of a deposit. But what's different are the compounding periods. Okay, so with our understanding of how interest works, I want you to think about how that's going to work. Which one is actually going to pay out a higher amount because it is an investment? Is it going to be option 1, 2, or 3? I want you to have a think about that. Pause the video, write down what you think the answer will be, and then we'll go through and figure it out. Okay, so for part 1, we've got $1,000 being invested every year, compounded annually. You'll notice that's actually the same as the question up here. The difference is we don't know how long the question tells us to do this for. So we're going to assume that because part A was for 6 years, let's do this one for 6 years. Okay? So again, going back here, that's why I've written annually here. Let's fill out period 0. We know that's at the end of the first year. No interest being calculated on that. Okay? So remember, our time is in months. So 12 is what we're dealing with. We need to keep all of our units consistent. Now, this is effectively going to go up to 72 again. So, whoop, there we go, 72. So that's going to be period 1, 2, I'll just type this probably quicker. There we go. There's our 5, technically 6 periods because we count period 0. The same process is going to happen. This time, though, it's actually a little bit easier because just like the previous one, we could just use straight 1.0575. We didn't need to do any division like in this cell, okay? Because it compounds only once a year and we deposit once a year. So it's equal to, I don't need the bracket, I'm going to put it anyway, 0.575. We're going to multiply that by our previous cell, because that's the one that's going to keep on building, remember. And then at the very end of each year, remember, we deposit $1,000. From there, drag and drop, there we go. Okay, so we can see that this came out slightly less than our one that we compound quarterly, but that's okay. I mean, that's to be expected, okay? Now we're on to the half-yearly section, all right? So, 500 invested every 6 months, compounded half-yearly. Again, the depositing time and the compounding time, you'll find they always match, okay? You shouldn't be getting any questions where they alter, but you never know, okay? I'll make sure I go through that in another video if we do run into those, okay? So again, just start by filling out period 0. At the end of that, 6 months has passed, and we have a total of $500 in the account. Now, it's every 6 months, so it's going to go 6, 12, 18, and we'll copy it down. How far do we need to go? Well, we're comparing them all like for like. They need to be in there for the same amount of time. So 72 is what we want, and sure enough, it goes to 72 for us, okay? You shouldn't get a question where they all have kind of odd timing. For an example, if we wanted to go to, say, only 9 months, we could do it for one of them, but these we couldn't, okay? Because they all have mismatched kind of periods. So I'll put this in, the number of periods. There we go, we got to 11 that time. And just like before, okay, we start entering the formula. This time we are actually going to need to do some division. So 0.0575, we have to divide that by 2 because the 5.75, remember, is for every year. We need to get it every 6 months. Then we're going to multiply it by our previous cell, and again, adding the $500. All right, dragging, dropping. There you go. So let's have a look. Which one came out the best? It was our original one. Okay, now the question does want us to graph it. So I'm just going to go over here, click on the cell here. Let's talk about the type of graph. I'd probably go with either a line graph or a scatter plot with the dots connected. I want a nice smooth line, okay, because it is compound interest. Let's go with this one. Now, obviously this is a blank slate. Just going to zoom out for a second just to get all of this in frame, and I'll make this a little bit bigger so we can see it. Now, I'm going to right click on this and we're going to go to select data. Now, there's a few series that we're going to add here. First one, let's add annually first. All right. Select the X values. Well, X is usually the independent variable. That'll be time. Okay, notice I'm keeping all the units consistent. If I had that in years, it's going to give me different numbers, okay? Because that might think when I enter it into the graph that it's 3 years. All right, so all months there. Now I'm entering the totals, hit OK, and there we go. We can see our annual, well, that shouldn't be the title, but anyway, I'll add a next set, which is going to be half yearly. X values we've got here, Y values, and notice I'm not using the periods as well for the X values, because obviously they have different values, and that's because of the different lengths of each period. All right, so already we can see some, starting off on a very similar note, but that gap is going to widen and widen. Let's add our last one, which is quarterly. X values, oops, went a bit too far, sorry, that should be 228, yep. Backspace this, the Y values, adding now, hit OK, and there we go. From there, I'm just going to add some chart elements. What we have here, I might just zoom in. Okay, shrink this down a tiny touch. Oh, chart titles are gone. All right. Well, this one is the time in months that has passed. Get rid of this. This is our total value of annuity. All right. What else am I missing? I'm missing a heading. So we want a chart title. So we had yearly, half, and quarterly annuity. Annuities, I should say. And there we go. We should put a legend in, but I'm not going to do that for now. Let's just have a quick chat about this. So as I said earlier, I'll just zoom in. Okay, so we've got our starting point. The Excel's been a bit frustrating. Okay, you can see that they kind of stagger their starts, and at the very end you can see where they're kind of differentiating from each other. And that's the whole goal of annuities, okay? Now, it might only seem like a small amount, but keep in mind, we're dealing with an annuity of only, $250 every quarter or $1,000 a year. You think of, some employees are going to be depositing hundreds of dollars a week or a fortnight or a month into their account. You're going to see this grow at a much higher exponential rate, all right? So, there's our graph for that one. I'll have this saved and I will add it to that style page for you. Okay, what we're going to go and do now is answer part C. So that should be C. There we go. Comment on the effect that changing the number of payments has on the future value of the annuity. When the annuity, or annuities I should say, similar payment amounts being made, just broken up obviously in terms of frequency. There we go. And that is how to use a recurrence relation in order to graph, plot, calculate any kind of annuity, okay? And you can see, well, I've already closed it, but with our table of values, you got the numbers. Anyway, this is the only lesson we'll spend on recurrence relation. It was just good to make that connection from a previous area of mathematics into annuities. Next lesson, we're actually going to go on to the hard-hitting facts of it. Thanks, guys.